Calculating z-scores. All right, a z-score. How many of you ever heard the term z-score before? Anyone? Like if you're reading an article in some magazine or sometimes even in the newspaper, it might talk about z-scores. Maybe not just in the general newspaper, but if you're ready to read any type of scientific study that's been done, it might include the word z-scores. Well, now you have a job, and that's to keep an ear out for it in everyday life, right? Okay, a z-score describes how far a data point, I'm going to call it a data value, is above or below the mean. And the mean is the average, of course. Okay? So a z-score describes how far a data value is above or below the mean of the data, the average of the data. Okay, these distances above and below the mean are basically just standard deviations. So last time when we talked about the normal distribution, we talked about how we can count standard deviations from the mean, right? And it covers sort of percentages, and that's, well, generally, like approximately. And that is, I just lost my train of thought. Anyway, last time that we talked about this, which wasn't last time, it was like last Tuesday, we talked about how we can count the number of standard deviations above and below and put those on our normal distribution so that we can figure out using the empirical rule what approximate percentages might be between here and here or here and here, right? So we've got the general idea. So now instead of saying that is 3 standard deviations above the mean, all we have to say is it has a z-score of 3. Or it has a z-score of -2. If it's 2 standard deviations below the mean. So we use positive z-scores for above and negative z-scores for below. It's just a quick way for statistics to kind of say how spread out the data is or where a data value fits in the scheme of things. Okay, it's just, I don't know why Z. I don't know why they use the letter Z. Might be an interesting little research project for you because I don't remember. I'm sure I learned it at some point. So, a z-score is found by taking the deviation from the mean. So notice how it doesn't say standard deviation, it just says deviation. So what that means is we take our data value and we subtract the mean. And that tells us how far away the data value is from the mean, right? So x is our data value and mu, that little grid coder, is our mean. So we're going x minus the mean, so we have the distance of the data value from the mean. Then we divide by the standard deviation. And that gives us the z-score. Oh, look, there's even a little thing there that says exactly what each thing means. Okay, let's practice this. The results of a common standardized test used in psychology research is designed so that the population mean is 130 and the standard deviation is 20. A subject earns a score of 152. What is the z-score for this subject's raw score? Okay, so we're going to start with our data value x, right? We're using our formula. So we're going to go 152 for the data value, and then we take the mean, which for this set of data is 130. So we divide by 130, and that gives us, what, 22? And then we divide by the standard deviation 20. And yes, we're going to get a decimal. Z-scores can be decimals. And that just tells us that it's like between 1 and 2 standard deviations from the mean, right? And how much it is. So go ahead and get a decimal for me on this. Pretty easy, 1.1. So that has a z-score of 1.1. I gave you a little picture, so if you wanted to draw it in, you can, but you don't. I don't know. Some of these statistics problems or normal distribution problems, I feel like drawing it out is almost a necessity. Or at least for me, I'm a visual learner. But other things, like this, just follow a formula. It's not a big deal. I mean, if you kind of wanted to figure out where it lands and just draw that picture, you can, but no pressure. You don't have to. So this would be like 130 and 152, and that's our z-score of 1.1 right there, or something like that, right? So it's a distance of 1.1 standard deviations above the mean. That's what that z-score means. All right, let's look at the next one. Pretty easy, right? We've done some pretty hard stuff. Kind of easy. The results of a common standardized test used in psychology research is designed so that the population mean is 125 and the standard deviation is 40. A subject earns a score of 29. What is the z-score for this raw score? Okay, so this time we take our 29, which is our data value, and we subtract our mean, which is 125, and we divide by 40 after we subtract it. What's going to happen in this problem? We're going to get a negative number, which means we're going to have a negative z-score, which means it's going to be below the mean, right? Okay, so math here, let's see, 29 minus 125, I'm cheating by looking at my completed paper. I got negative 96, what do you guys think?
Got it too.
Perfect, and then we're going to divide that by 40, and go in twice and a little bit. What's our z-score? Negative 2.4, excellent. Again, if you wanted to kind of show that on your graph, not necessary though. Okay, so that was a fairly low score in the scheme of things, right? Because we're to follow the normal distribution and the normal percentages and stuff. That score of 29 is rare. All right, the results of a common standardized test used in psychology research is designed so the population mean is 100. The standard deviation is 40. Determine the score that corresponds to each z-score. Then determine what percent of the data is above and below this score. Oh, now the problems are sounding difficult. I feel like we have to work backwards. And then, do you get the impression we're using the empirical rule? Probably. All right, here we go. So, working backwards, we would take our formula, which is our z-score is equal to our score, whatever you want to call that. We're going to subtract by 100 and divide by 40. So we're basically solving that equation. How do you like to solve equations when you have fractions? Or division in the problem? Well, yeah, multiply it, like cross multiply, sort of, but we don't have a fraction on both sides, but it's sort of the same idea. We just can multiply both sides by 40, right? Okay, so let's start with that. So we're going to have 40 times 1.5 equals x minus 100. So now how do we find that score? We're just taking the formula we just learned and used a couple of times and working backwards, right? Anyone calculate that one for me? $160. Okay. Now we're supposed to figure out the percent of data above and below that score. I didn't write down on here how I did that, so I'm wondering if I did it using a table. Because it's 1.5, it doesn't fit exactly within our empirical goal. Because it's not like at 1 or 2 or 3, right? Like we were used to doing on that empirical goal assignment. So this is a little bit trickier, and I need to refresh myself on the process for finding the percents above and below. So if you'll be patient with me, we'll come back to this. Okay? So let's go ahead and I'm going to let you practice this one, though, really fast, finding the score. I want you to find the raw score on B for me. negative 2.1 z-score. Go ahead and work through it just like I did the last problem. Do it on your own. I'm going to go through it with you. So we're going to do what we did in the last problem. We're just going to take basically our 40 times our z-score. So 40 times the z-score, which is negative 2.1. And that's going to be x minus 100, right? Since we're using the same set of data, it's going to follow the same number procedure, like standard deviation is the same number, mean is the same number. So I could have just written it out with the plus instead. So 40 times negative 2.1, and then we're adding 100 to that. So let's see what we get.
Negative 184.
Okay. Is that really what it's going to turn out to be, or did I do something wrong? Let's see what my paper says. So my paper says 16. Right, because you're adding the 100 in, so it actually might be that maybe you accidentally subtracted the 100. Would that do it? No, that wouldn't be it either. Okay, so of course I made a mistake.
Oh, I made a mistake.
Good, we all make mistakes. I mean, good. Okay, we got it. I'm glad you figured out what you did. So negative 16 for the win. So if you want to show on your graph what all this means, you've got, oh, it's positive. My goodness, I'm getting all sorts of confused. It doesn't make sense to have a score that's negative. What would I do without all of you? Okay, so we have 100 at our mean, and then at 1.5 it was 160, and at negative 2.1 it's 16. That makes sense, right? Because our score on the actual test is going to be a positive number, correct? So, okay, we will come back to these percentages short